David Sugar here. Welcome to the channel. Today's all about systems in equilibrium, when systems aren't moving, when they're not in flux and in a steady state. And this is chapter 5 of the book, The Science of Systems. If you want to learn more about the book, The Science of Systems, you can go to davidsugar.com/book. There's a free downloadable PDF. Additionally, you can go to Amazon and buy the paperback if you want to see it in person. It has lots of figures and is really engaging, so definitely suggest that you check it out. So what is a system in equilibrium? One equation that can be used to understand this is to consider a system that follows the equation that the change in a quantity x equals 0. Now the change in a quantity x can equal x in a final state minus x from an initial state. So when the final state and the initial state are the same, there'll be no change in x. Now sometimes x can grow, sometimes it can decrease, but when it's the same, the change in this quantity is what we call an equilibrium. It's not in flux. So systems can have a lot of different quantities, that remain in equilibrium. And the patterns of equilibrium is a really good foundation for understanding systems, and which can then be brought up to systems in flux and changing other systems. But this provides a really good grounding to say, well, let's just study quantities that don't change, that remain in equilibrium. One of the classic examples of something in equilibrium is that when something is structurally stable, it means all the sum of the forces equals 0. So that there's not some type of force that will move it down, like the force of gravity or something. Everything is being balanced. And so this means that there's no acceleration, right? It's not changing. So this can be thought about, for example, as a steady arc. And this steady arch, each of the vectors, which are represented by arrows here, are balanced at each of the points. So the center stone is balanced by the other stones, or balanced by the other stones. And so this means that the total acceleration is 0. It's being held there. Now, if one of the stones fell out, the force of gravity would pull that stone down and it would collapse. So equilibrium is really important when it comes to geometric stability and building construction and using this for engineering. Now, vectors, in order to define these vectors and understand forces, it's really important to establish what is the coordinate system. One of the very basic coordinate systems is the Cartesian coordinates. And this has the x direction, which can be thought as horizontal, the y direction, vertical, the z direction, in and out. And this can define a three-dimensional volume. Importantly, each of these axes are orthogonal to one another, means that they're right angles. That means the change in one doesn't influence the change in others. And this is essential for mathematics, and a system in equilibrium, for example, would mean that the vectors sum to 0 along each axis. There's no horizontal, there's no vertical, there's no in and out. When all those sum to 0, that means it would be stable. Now, there can be other types of coordinate systems, and this could be relevant depending on what kind of system you're studying. So if you're studying a cylindrical system, this has the horizontal angle, the radius to the cylinder, and then the height z. And these are also all orthogonal to each other. So the change in one doesn't influence the change in others. Another really useful coordinate system is spherical coordinates. This has horizontal angle and vertical angle, as well as a radius. And so this also is orthogonal. All three of these axes don't influence the other one. And this can be really useful for studying like a planet or a spherical symmetry like atoms and lots of other things. These coordinates make it easier to do calculations. So all three should, in any other coordinate system that are orthogonal, they should produce the same results. But depending on what system you're studying, you may study one or the other. Now, to give some more tangible examples of vectors, imagine a trajectory of a ball. Now, the horizontal velocity could be represented by Vx, right? The velocity in the horizontal direction. Now, the vertical direction can be represented by Vy, the velocity in the vertical direction. Now, in a trajectory of a ball, for example, the horizontal direction velocity is staying almost exactly the same. It might be slowed down a little bit by air resistance, but generally speaking, if you're not using air resistance, you say the horizontal velocity is the same, on Earth with gravity going down, But the vertical direction, it starts going up. There's a velocity going up, but the force of gravity accelerates that and changes the velocity so it goes back down. And so vectors allow you to calculate this, and the total velocity, you would square the sides of Pythagorean theorem to find the total hypotenuse between the distance and the rise. Now, another way to think about vectors is not just for one point or one object moving along, but for a whole field. So what is the vector at each point of a field? An example of this is like the Earth. So imagine the Earth as a spherical planet. And now we want to calculate the vector, the force of gravity at each point. If a test particle was placed at each point in this field, what force would it experience? Now, the direction of these vectors all around the Earth should all point to the center of mass of the Earth. Additionally, as it gets closer and closer to the Earth, the vectors increase. That means the arrows get longer. So this is really important that vectors not only describe, trajectories of individual particles, but get a whole field of what is the vector at each point in a space. So calculus was a revolutionary, advancement in mathematics that really helped Newton understand the trajectory of planetary bodies and calculate a lot of other really interesting things. Now, the key part about calculus is to understand the derivative, here represented d. And so the derivative of f of x divided by the derivative of x, what that is the infinitesimal rate of change. So what is the change in the height divided by the change in the width? And that's usually the slope. Now what the derivative is to say, okay, take this, but make the change of the width approach 0. So what is the slope as the change in x that is approaching 0? And so this gives the infinitesimal rate of change, which can be thought about as a slope. Now, taking the derivative, the opposite mathematical operation is taking the integral. And that basically goes the opposite way. From the answer from the derivative, if you take the integral of that, it goes back to the derivative. Now, if there's a line, for example, one way to think about this is that the derivative of the line is a slope. But the integral of the line is the area, the area that the line traces under. So we'll see more about this later on. So another really practical way to understand what a derivative is doing is it can be thought about as the rate of change. So imagine there's just like a bathtub or some stock of resources. Now the stock, the flow rate is how that stock changes over time. So that can be thought of as the derivative over time. How is that stock changing over time? And the derivative will tell you at each instant, right, infinitesimally, how is that change going, which is basically the flow rate. Now the total stock can be thought about as the flow rate from the beginning, the integral to that part of time. There may be some initial stock that was added, but assuming all the stock was added through the flow rate, like an input, for example, you take the integral from the beginning all the way to a given time t, the integral of the flow would give you the total stock. So it's going the opposite direction. Now you can use this in stock and flow diagrams where you can have different stock of resources and different flow rates between them, and you can calculate the overall effects and how they interact with one another. But this is a really practical way to use calculus and a way to kind of understand how it works. The stock is basically like this bathtub of water, and the flow rate is either the drain or the faucet. How much is it changing up? How much is it changing down at a given time? So one really interesting use and really practical way to understand a derivative is through partial derivatives. And this is saying, let's just change one axis while keeping the others constant. And this can understand, rates of change in three-dimensional spaces. So one example of this is something called the del operator. And the del operator is this kind of like upside down triangle. And it's basically saying, what is the partial derivative along x, the partial derivative along y, so the rate of change, of x, the rate of change of y, the rate of change of z. Now, to just give an example of this, and this is more as two inputs, let's imagine is the f of x and y describes a mountain. So basically the f of x and y can be thought about as z, so the height at any given point. Now, if you take the gradient, which is basically the partial using this del operator, and you put it on the function of the mountain. That's understanding the slope on the mountain. So basically, at any point on the mountain, what is the greatest rate of change? And this basically allows you to understand which direction would water flow, right? Water would flow the opposite of a gradient. We often use the term gradient to describe a hill's steepness, right? So the partial derivative is really useful because it's not just looking at a line, for example, but it's looking at a space. So now if we have a two-dimensional surface, different heights, you take the del operator, the partial derivative along x plus the partial derivative along y, for the x and y axis, that gives you the exact vector for the greatest increase on that surface. And if you take the opposite of that vector, that'll show you how water will go down. So partial derivatives are really, they can be extended, 3 dimensions, 3 inputs of f of x. So it's really useful to understand lots of like volumetric surfaces and bring the notion of vectors, not just one point, but entire field. So this del operator is used all the time in physics. And I want to describe some of the really 3 common ways it's used. So one is the gradient, which we just saw, which is the slope of the direction. So this v is saying, let's say, imagine a vector field. We call it v. So when you just take the del operator right next to the vector field, that's called the gradient, the greatest increase of slope. And this vector field can, just describe 3 dimensions, something f of x, y, and z. Now the divergence is using something called the dot product. And that's just saying we're going to take the del operator, all the partial derivatives along x, y, and z, use something called the dot product on the vector field. We won't go into exactly the mathematical notation of this, but I want to describe the geometric meaning. And basically the geometric meaning of the divergence is the flow in and out. So if there is an imaginary sphere, what is the flow in and out? Now the curl uses something called the cross product. It uses all the partial derivatives in the del operator for x, y, and z, cross product the vector field, and that describes the amount of twist, the amount of rotation. So we can see how this interacts in the next slide. So for example, let's consider a static electric field and a static magnetic field. So a static means it's not moving. So, something in equilibrium. And so a static electric field, you can see that the divergence is proportional to the something rho, which is basically the electric potential. So how much electric potential is there? So there's greater electric potential, more charge, more divergence, right? There's no cross product. The cross product of the electric field is 0. The divergence is proportional to the amount of electric charge. Now the magnetic field, and this can be seen because the field lines go directly out on a charge. Either they're going out if it's positive or in if it's negative. There's a flow, but there's no twisting. But in a static magnetic field, there's no divergence, there's no in and out. All there is a twist. And it's basically proportional to J, the current. So more current, more twist. Less current, less twist. But there's never a divergence. So this shows you the stark differences, right? So static electric fields, all about divergence, in and out. It's similar to gravity, it just points in and out. Magnetic fields, on the other hand, are completely different. They're all about twisting, all about curls. And this, del operator is the key thing that can be used to understand it. So, wanted to show this. And I'll just note that, moving electric and magnetic fields can kind of self-induce each other. We see this with light. So this doesn't describe dynamic electromagnetic fields. That's a kind of a different theory, but this just describes static electromagnetic field. So once they're dynamic, they can be described as one electromagnetic field, but that's in a dynamic case. But this is the static case. So Laplace's equation is basically saying, let's take this idea of a derivative. What about the second derivative, the derivative of the derivative? So just first, let's understand this with one variable. So imagine it's d of x divided by d of y. But now we're taking the second order. So it's d squared of x divided by d squared of y. So d of x divided by d of y could be thought about as a slope. But the second order derivative is how much is the slope changing, the rate of change of the rate of change. Well, if it's a straight line, there's no change, right? There's just one slope that's there the whole time. It's not curving up, it's not curving down, it's just one line. So when the second order rate of change is not equal to 0, it means that the slope is changing. So maybe the slope is increasing, the slope is decreasing. And then what you see there is there often a potential for a maximum and a minimum. And what Laplace between two boundary points. But what Laplace's equation is saying, let's take the second order derivative of the del operator. Well, remember the del operator was looking at the partial derivative of x, the partial derivative of y, the partial derivative of z, but now it's saying the second order. So the second order change in y, the second order change in z, x, a second order change in z. And this has a key connection to equilibrium, as we'll see. So one really interesting example of this, imagine a square ring was dipped into soap film. Now, when you pull it out, and let's just say it's a flat square ring, basically what we see is that that whole surface follows a Laplace equation. Between the boundary port, there's no mins and maxes, right? It's just a straight line. And that can be thought as a minimal surface. Now, if you bend that square ring with the soap film, it would change, right? But it would change in such a way to still minimize the distance. It wouldn't create extra little bumps and extra little dips. And if you actually calculate, it follows Laplace's equations. So basically, there's no extra dips, there's no extra bumps. So the bottom example shows an example where Laplace's equation is not followed, right? Between the boundary points, there may be an extra bump and extra dip. Now that may describe an energy, and we'll see energy is all about breaking this equilibrium, but in a state of equilibrium, it follows Laplace's equation. Now I'll just make a side note that soap films, like without enclosed on a ring, just like a bubble, can self-enclose. And so it doesn't necessarily always follow Laplace's equation, but it does minimize the surface, and it follows other equations to create minimal surfaces. So that's another cool thing that can be seen in the geometry of soap films. So practically like almost every field in modern physics, like a lot of them, when they're not changing, if they're in a static state, they usually follow Laplace's equation. So for example, if there's just like a planet and a gravitational field, that planet, represents a maximum of energy, and there might be a minimum out there, but the curvature of the gravitational field is smooth. There's not extra bumps and dips unless there's energy. But without energy, if it's in a state of equilibrium, it settles to that smooth state. Even if it's like a burning candle, but imagine a hypothetical where it's just a perfect amount of heat and it's being dissipated off completely equally, not, extra flames and turbulence. If it's in a static state, heat itself also, equalizes in the Laplace's equation. Like when heat is in equilibrium, even if it's dissipating and it's in a steady state of dissipation, you're not just going to see a little bump or a little dip. It's going to be completely smooth. So it's all about smoothness. And even this can be seen in non-viscous streamlines. So like even when water is moving around an object, and now let's say the streamlines, but it's in a state, imagine where the streamlines are not moving anymore. It's a steady state. So it's a steady state of the flow lines. Well, those flow lines in a non-viscous fluid would actually follow Laplace's equations, right? They would all be evenly and smooth. There wouldn't be extra dips and extra bumps. So basically, this is saying that a lot of the fields that we see, like even the electric field, gravitational field, heat, non-viscous fluid lines, when they're not changing, they're following Laplace's equation. So this is describing how a lot of natural systems behave in a state in equilibrium. So going back, we talked about this stable arch, and a lot of the other forms that we see in nature, they have to be in equilibrium, or they would, explode or implode or something like this. So for example, for the star, there's the outward pressure, hydrostatic, pressure of the sun. And there's also the inward pressure of gravity. And it's all about finding that balance, right? Where the star is that balance. If there's more gravity, it would get smaller. If there's more pressure, it would get bigger. This can also be thought about in terms of like a planetary system. You know, there's just enough centrifugal force to counter the gravity. That's how it stays in a stable orbit. If there's less centrifugal force, you know, it would spiral into the center. If there's more centrifugal force, you know, this is a hypothetical force associated with spinning, it would fly out. And even in the atomic system. Now, these are a little different because these are like wave orbitals. But it's when atom like has 2 positive charges and like 2 electrons, it means the electric charge is equalized. And it doesn't have a tendency, you know, to want to grab another electron or have too many electrons and want to give one off. So that's a much more stable form. Those are often thought about as like the noble gases when an entire energy orbital is filled and it's in neutral atom, not like an ion. So these are all examples of how systems we see in nature are able to reach equilibrium. It's all about balancing the forces. So another really interesting thing about like equilibrium and like a stable pattern is this idea of a catenary curve. And this can be thought about as like hanging a rope or other string-like object. Now, these don't necessarily follow Laplace's equation because you can see there's one dip. But the thing is, it's not like lots of bumps and dips. It's one smooth dip, you know? So it's not Laplace's equation, but it's one smooth deviation. And this constant C can be thought about as a different constants, like is a tighter string or looser string, for example, between 2 boundary points. And you can also calculate, for example, if you move one side of it down, then the string will kind of move in a different way, and you can use forces to calculate that. It's basically saying, you know, imagine a string with equal weight throughout the string, and the force of gravity is pushing down each side. What's its optimal, you know, geometry of stability? Now, there's a really cool thing about catenary curves, which is that when it's held upside down, it's pure tension, the resistance to outward pulling forces. Now, then there's 0 compression, and the idea of compression is, you know, resistance to inward pushing stresses. So like a string, for example, has 0 compressive strength, but it has tons of tensile strength. So catenary curve, where you hold it, it's all about the tension. It's 100% tension, the geometry, there's 0 compression. Now, what's interesting, if you flip it, you can now make an arch that is 100% compression and 0% tension. So it's all about the other forces. And so this creates a geometry that's really, really stable, right? There's no extra tension forces in the arch trying to like pull it apart. Everything is completely held in pure compression. And so this is a really strong form. So basically, like this can be seen in like Spanish architecture, for example, where they would hang a string between 2 points, get the curve, flip the curve, and then use that for the arch to support the stairway, right? So there's some really interesting things, and Gaudi in Spain used this a lot, even to design the Sagrada Familia, which is this huge temple. He basically hung all these chains with different weights on them, and then looked in this with a mirror to flip it. So the structure was held with tons of compression and 0 tension. This is an interesting way that we can use like equilibrium forms to design really stable patterns in nature. So another idea of stability, equilibrium, and this is a deep, deep principle in physics, is the principle of least action. And this is to say that out of all real trajectories, or of all trajectories that could be, the one that's real, the one that happens in reality, is the one that minimizes action. This can be thought of when the change of action is 0. This is basically a minimal action point. So that the trajectories we see, the various patterns we see in nature are ones that minimize action. Now, what's action? There's a more technical physics definitions that we'll get into in a second, but the units of action can be thought of as mass, speed, and distance, or energy times time. So for example, for a given mass at a given speed, action is minimized when the distance is the least. So imagine there's an object flying at a given speed. Well, action between 2 points, you know, like the initial state and the final state, you can take any trajectory, you can go around in circles, lead to the final state, you can go back a little bit, lead to the final state, or you can just go in a straight line. Well, we'll see that the straight line has the shortest distance between 2 points, right? So that's the one we see. If an object is freely move into space, it's going to go in a straight line because the distance is minimized for that given mass at that given speed. So that basically means that the action is minimized, and this follows the principle of least action. Another example is that the energy over time. So given a given time interval, which trajectory would minimize energy, right? So if you have water, water is not naturally just going to go creep up a hill, increases potential energy. It's going to want to decrease its potential energy, right? It's going to want to move down. So basically, like, the energy is going to want to be reduced for a given amount of time. And so this can understand lots of the patterns we see in nature. Basically, everything at its core is really trying to minimize action. And action, there's a more technical definition that uses this term L, which stands for the Lagrange. And that's basically the kinetic energy minus the potential energy. And if you integrate this over time, you get the total action. So it's around the differences of kinetic and potential energy. You integrate that, you get your action. Well, it turns out in physics that when action is reduced, that's how you figure out what equations of motions really work out of all possible ones. And this is seen in all areas of physics, classical physics, thermodynamics, quantum mechanics, even relativity. In each of their respective fields, the notion of action being reduced, something of a principle of least action being followed, is adhered to. Each their own ways, they each have their own Lagrangians, own different types of energy and such, but the principle of action is always followed. So this is a really deep principle in physics related to equilibrium. So symmetry can also combine with the principle of least action to lead to some of the most fundamental laws in physics, which are these conservation laws. So one of these symmetries is space translation. And basically this is to say that a given experiment should result to the given outcomes, the same initial conditions should result to the same outcomes no matter where you are in space, right? Like physics or science more generally shouldn't care if I do it here or if I do it 5 meters to the right. It should be symmetrical to any place. Additionally, it should be rotationally symmetrical. If I do experiment this direction, if I rotate the other direction, it shouldn't change the laws of physics. I mean, yeah, maybe some of the values of the coordinate systems would change depending on what your perspective is, but the actual results would not change. So no matter what I picked my coordinate system, it would give me the same results. That means it would be symmetrical for any rotation. That the laws of physics wouldn't be different for facing up or rotated down. Also, time translation. Basically, the laws of physics should remain the same now versus the future, that they shouldn't change. Now, different parameters in physical laws can change, like the amount of total dark energy at a given time would change as the universe evolves, but the equations around dark energy in the universe shouldn't change. So it's okay for like entropy to increase, for example, but laws of physics themselves, there shouldn't be a different equation for entropy in the future, for example. Now, what's really interesting, this is called like Noether's theorem, which is a really famous theorem, which is basically to say if you consider like this different continuous differential field, which is basically saying this kind of like vector field, a whole smooth field of different values that can have differentials, different calculus, that one that's follows the principle of least action and is symmetrical for any space should also have a conservation of linear momentum. So that the momentum, which relates to the total mass and velocity, which can be thought as almost kind of like a form of energy, the linear momentum should change. That when the principle of least action is followed for a field that's rotationally symmetrical, angular momentum should be conserved. And that is symmetrical for a time translation with the principle of least action means that the total energy should be conserved. So conservation of energy and momentum, right? These are really, really critical things. But what Noether's theorem really found was this can be thought of as almost like a byproduct when you have these deep, deep symmetries, which are assumed, also part of the unity of science, that science shouldn't change depending on your location, rotation, or time, place. But combined with the principle of least action that we just saw there leads to the conservation of laws. So principle of least action is really important. And like, for example, Newton law, like F equals ma, with the principle of least action, you can find that law. So it's actually, because, you know, when it doesn't follow the principle of least action, you know, Fm equals ma is not necessarily followed. So other things can occur. So wanted to make this connection. This is like really deep and fundamental in physics about how we think about symmetry, least action, and these conservation laws, which are really essential. So just to give you an example of like how these conservation laws can be used to calculate states. So, you know, something's in equilibrium. That's what really conservation laws are trying to find. So, you know, they have these initial states of these objects, they interact, maybe they smash into each other, we have these final states. Well, can we find something that doesn't change? Well, yeah, the total energy, right? The total energy of the initial state is going to equal the total energy of the final state. Well, additionally, the total energy of the momentum, the total momentum of the initial state and the total momentum of the final state would also be at equilibrium. They won't change, you know, linear momentum and angular momentum. So for example, if you know the initial states and you know one energy in the final state of the other object, you would know the other object, because what you're expecting following the laws of conservation is that the total energy and the total momentum would be conserved, would be at equilibrium, would not change. So what this is, symmetry, equilibrium, principle of least action, you know, it's really trying to find what is not changing in nature, and then how can we use that to formulate some of our deepest physical theories. So want to switch gears a little bit and talk about another kind of equilibrium, which is really an interesting one that's kind of mind-boggling, which is that even if you're in a frame of reference that's like accelerating or not accelerating, the speed of light is always the same. So a car that's not moving turns on its headlights, it goes the speed of light. Now the car's moving half the speed of light, it turns on its headlight, and I'm still seeing the headlights going the speed of light. You know, it's not like 1 plus this half, 1.5 the speed of light, you know, what you would expect following Newtonian mechanics. So one way to rectify this, you know, a theory developed by Einstein was that, you know, assuming that the speed of light is constant at every reference frame, there's new kind of equilibrium. You know, there's a new kind of equilibrium. The speed of light's always constant, even if you're accelerating or not, even if you're going at high velocity. Very weird. Well, if you just had a box that you saw, like imagine you're inside of a box and you see a beam of light going top and the bottom. Now, if that box is moving across, you would see it would trace out a longer beam. But now there seems to be an inconsistency, right? I've seen the speed of light move a longer distance when it was moving the object, but if I was inside of the object, it looked like it went a shorter distance. So how do we rectify, you know, the speed of light's always constant? Well, it could be that time itself is dilated. So basically, if you look at this formula, you see the dilated time versus observed time, you can get a triangle, and then you can use that, you can use the Pythagorean theorem, and you can calculate how speed influences the time. So basically, assuming time is changed, while the speed of light represented by c is not changed, you can make this triangle work. And essentially, that's what special relativity is all about. It's saying that when you start moving fast, basically time is dilated, time moves slower. And this can actually be seen with like subatomic particles have a certain decay rate. When they're moving really fast, their decay rate is a lot longer. They're slowing down, basically. Now, not only is time dilated, mass is also increased. So as you go higher and faster, closer and closer to the speed of light, your mass increase, the dilated mass. And this is also why it's impossible to go faster than the speed of light, because as you keep on pushing the object, it gets heavier and heavier and heavier and requires infinite energy basically to get above the speed of light. Another really interesting thing is that distance itself is dilated. Like a ruler that's 12 inches moving, basically near the speed of light, the 12 inches would be shorter than the same 12-inch roller not moving. So relativity introduced a lot of new things about physics and not a lot of new things about what is being held in equilibrium. Because this needs to be represented basically by, instead of a 3-coordinate system of x, y, and z, you also need time. And this is called like a space-time coordinate. Now, a lot of the things that we thought were held constant using Newtonian physics, actually, when you consider these dilations of special relativity, you have to think in terms of 4 vectors. And this also simplified a lot of other things, but showed that there's other quantities that remain conserved when you're thinking about space and time and relativity. Now, another really interesting subsequent theory by Einstein, general relativity. And this is all about frames, accelerating frames. And one of the key results of this theory is that energy mass curves space-time. So what do you mean by curvature? Well, let's imagine a triangle on a flat plane. When there's zero curvature, that's of a triangle, all the angles add up to 180 degrees. Now, if it's positive curvature, like almost the top of a sphere, for example, that same triangle now, the angles could add up to more than 120 degrees, right? The lines would be bent inwards, it would curve, and so those angles would get greater. Now with the negative curvature, it's almost the opposite. It's like pushing down almost to like a saddle. And then this would be negative curvature, so the lines would go inwards and the angles could be less than 120 degrees. Now the key effect of general relativity, there's lots of other implications and things, but that energy and mass basically curves space and time, so it makes trajectories that are normally straight curve towards the energy and mass. And these are still straight lines, right? That's the interesting part about curvature. So even when we see things moving in a curve or trajectory in gravity, technically they're moving in a straight line in the curved space-time. So another analogy for this is, imagine you've seen a map of how airplanes fly over the world. Now, airplanes, it's a spherical globe, they usually just fly in a straight line, right? They might leave a destination and fly in a straight line, or leave another destination, fly in a straight line. It's pretty obvious they're going to straight lines when you look at a curvature. But now if you make a flat map, you would see that these airplane paths are curved in all these interesting directions. And that's because the map is flat instead of curved. So essentially this is happening with gravity, but with another dimension up. Where basically the trajectories we see look curved in 3 dimensions, but in a space-time, you're actually moving in straight geodesics, where they're minimizing. The path that they're moving follows the principle of least action. It's not adding more energy, it's not curving or whatever. It looks curved, it looks like a trajectory, but it's actually moving in the most efficient path, similar to the planes flying over the globe. So these are called geodesics. So relativity also allows one to study and leads into modern cosmology. And one of the big effects of this is, one of the discoveries is this Hubble expansion, basically. And the Hubble constant explains how fast the universe is expanding. Well, bringing this back in time, and there's other evidence for this, modern cosmology expects that the Big Bang happened something around 13.7 billion years ago. And this essentially was the beginning of the universe, exploded, space-time increased. And now, basically, the present observer, when we look back into space, we're seeing light from the past. So, stars that's 10 light years away, when we see the light today, that light is 10 years old. So you can look farther and farther back. It's looking kind of back in time. And then if you look really far into the universe, it basically is like the afterglow radiation, which is like earliest time after the Big Bang. And so we're receiving light, as more and more light from further distances over time. And this can be thought about as a light cone. So this light cone usually would expand, but because there was a Big Bang, it curves back into this like pear-like shape, where basically all the light, no matter which direction you're looking, up, down, left, or right, it leads back to one point, right? If you're looking back and back into the past, eventually that would all lead to the Big Bang. Now, in this light cone diagram, the horizontal direction is space. It should be noted that this is a 3-dimensional slice of space, right? So this is all compressed, and then time's on the other direction. But at a given today, when the observer, interestingly, each observer is also the center of their observable universe, of their light cone. And so basically, the observer looks up, down, left, or right. The radius of this expected universe right now is 46.5 billion light years, this radius of this sphere that we see in the observable universe. And, it might be kind of weird. Okay, why is this sphere that we see today bigger than 13.7 billion light years? The Big Bang happened 13.7 billion light years ago. Well, there's like dark energy in the expansion. So there's other kind of interesting things where the universe was expanding too. So then we can see farther back. So there's lots of interesting kind of like mind-boggling things. We're just scratching the surface on some interesting findings. But thinking in terms of light cones, thinking in terms of curvature, this is some of the results that general relativity really gave some theoretical backing to and allows us to understand the universe at the cosmological scale. So there are some key quantities in physics that are posed to be conserved. Some of these we saw earlier, like the conservation of energy, the conservation of momentum. There's also the conservation of quantum information and other lots of cool things. Now, one way to draw this in physics, for example, is just imagine the universe as this box. And the conserved quantities in this box would remain, the change in these conserved quantities would be equal to 0. Now imagine that there is a closed system and an open system. The closed system has no change over the boundaries, while open system does have change over the boundaries. Well, these quantities that are expected to remain conserved in the universe has key implications for closed and open systems. So for a closed system, if the change in the conserved quantity is 0 inside the system, everything in the universe not in that system, so the universe minus that system X, for example, the change in those quantities should also be 0. So if there's a closed system, if the change in conserved quantities is 0 inside of it, everything outside of it must also be 0. Otherwise, it wouldn't be conserved, right? The universe, it would grow or decrease or something. Additionally, this can also be thought about in terms of an open system. So if the change in conserved quantities is not equal to 0, so there's a flux over this open system with conserved quantities, like imagine an input energy, then the universe, everything outside of the system in the universe must also have a change. So this is basically saying you don't get free energy, right? If energy is conserved, energy is not just instantly coming inside of this boundary from nowhere. That would break the conservation of energy. It would only go inside of that system if it was coming from the outside the system. Or if there's an open system, energy is leaving. It's not that just left the universe if energy is conserved following that assumption, but it must also go to the environment. So universal conservation has key implications, for open systems, closed systems, and thinking about what is conserved at that universal scale. We were just looking at cosmology, relativity. There's other kind of interesting things that can be conserved. But physics is often about thinking about this and which systems are closed and which systems are open to certain quantities, and which ones are conserved over time and which ones aren't, because there's lots of things in the universe that are not conserved either. Like entropy is expected to increase the total order. So next chapter we're going to go into things that are not conserved, but wanted to highlight some of the things that are this chapter. So thanks for coming and tuning in. This chapter was all about things that are conserved, equilibrium, understanding a little bit more about vector fields, some basic introductions to relativity, which we'll build upon later, setting a lot of groundwork for thinking about systems, static systems, static electric fields, static magnetic fields. A lot of them follow the Laplace's equation, general smooth curves. And next, we're going to look more into flux. And this is when a lot of these Laplace equations are broken. Things are changing over time. It's not a stable system. The arches are not being held. It's being moved. So tune in for more. And if you want to learn more, go to the website to download a free PDF. And Amazon has the book, The Science of Systems. See ya.